10.1, radical expressions and functions. For this first example, let's go ahead and find functional values for the function we are given. So we're given f of x equals negative of the square root of x plus 1 squared. So to find f of negative 3, we'll just go ahead and substitute negative 3 into our function wherever we see an x. So that is the negative of negative 3 plus 1 squared, which equals negative of, let's simplify the parentheses, that's negative 2 squared, which gives us negative of the square root of negative 2 squared is 4. Now we know that the square root of 4 is 2, and we want the negative square root, so it's negative 2. Let's go ahead and do the same function, but now find f of 4. So that'll be negative of the square root of 4 plus 1 squared, which is negative the square root of 5 squared, negative the square root of 25, which will be negative 5. Okay, we want to simplify each one of these expressions. So please keep in mind now, I'm hoping you've already gone over the section, when you're taking an even root of an expression and the final answer has an odd exponent, then it's necessary for us to use absolute value bars, because remember, when you're taking an even root, you have to look at the sign in front, and the sign in front, if there's nothing there, that means it's asking us for a positive answer, the principal root. But excuse me, but if the answer actually has an odd root, or sorry, odd exponent, then the variable could very well represent a negative. So therefore, to confirm that our answer will actually be a positive, we have to include absolute value bars. So here we want the square root of 8 minus t squared. So we have two factors of 8 minus t. We're looking for a pair, so that would simply be 8 minus t. Now notice this was a square root, and we ended up with this expression, which really is simply a power of 1. Therefore, this t could very well make this a negative. So that's why we will go ahead and add absolute value bars. Now here, we want the fourth root of 625, but we also want the negative of that. So in this case, we don't need to worry about absolute value bars because we are looking for the negative answer. So we can go ahead and bring down the negative, and we're looking for a number multiplied to itself 4 times in order to get 625, which would be 5. Here, remember this number here is very, very important. This is the index. This tells us how many per group we are looking for. So in this case, if I have 414 factors of the entire factor of a plus b, how many groups of 414 can I pull out? Simply 1, right? A plus b. But now, this was an even root, so that means that I was looking for, if you look at the sign in front, there's nothing here. We're looking for a positive answer, but a and b, a plus b could be negative, so therefore we will have to put absolute value bars. Now in this one, we can't take square roots of each one of these individually, because remember, you can only take square roots of factors or roots of factors. So let's see if we can factor this. This is actually a perfect square on the inside. 9x squared minus 30x plus 5. If we factor this, we end up with 3x minus 5 times 3x minus 5. So now we want to find a pair of the same factor, which in this case we do have 3x minus 5. So we'll put 3x minus 5. And we wanted a positive, the principal root. So this could be negative, therefore we'll put absolute value bars. And these last two. Now you don't always want to just go ahead and put absolute value bars, because notice this one. Here we're looking for a cube root of negative 125y to the power of 3. A cube root means you're looking for something, an expression that was multiplied to itself 3 times. If something is multiplied by 3 times, it could very well be negative, right? Because every 2 makes a positive, and then the third one could make it a negative. So in this case, let's go step by step. We want a number multiplied to itself 3 times to make negative 125. That would be negative 5, and then y cubed would be y. And let's go ahead and find the domain here for the function f of x equals the 4th root of x minus 9. So if you remember, anytime you have an even root, the only way that this would be possible to find an even root is as a real solution would be if the inside is a positive. Why is that so? Because an even root implies that you're looking for a set of factors that appear this number of times. If it's even, that means everything has to pair up. Well, every pair ends up being positive, right? Because we know 2 negatives make a positive. So it would be impossible for the inside to be a negative. Therefore, anytime you have an even root, you just say, take the inside, which is x minus 9, and you have to confirm, just like I did in class. If we break our number down into 3 parts, if it can't be negative, what can it be? It can be 0 or positive. So we set it greater than or equal to 0 and solve. So x is greater than or equal to 9. So we can write this in interval notation or set builder notation. Now, if this were an odd root, then your domain would be all real numbers, because odd can have negative or positive on the inside. It doesn't matter.